Welcome back. It's yet another exciting installment of Missing Data, although this time I think it's a little bit more practical. To summarize class up to this part, it's been nothing but roadblocks. So I think what you could understand about missing data is that really you should never have missing data. If you never have missing data, then this is a problem, right? The end. Solves every problem. No. How would you describe what we've learned up to this point? Yeah. How would you describe what we've learned up to this point? Mhm. That's good. I'm going to put a different spin on it. Oh, go on. Yeah, yeah. Hmm. Yeah, that's right. That's right. I would describe missing data as a very difficult problem to solve, and nothing that we've learned up to this point has solved it really exactly. Right. So in SEM, our problem was not all SEM, the SEM framework, the ML framework. That sounds fine, but it doesn't, number one, doesn't fit all of your models. Number two, if you've got an outcome that's not continuous, you start getting into problems. So we're like, oh, wait, Bayes will help with that because we can specify our likelihood better. But then we saw last week with JAGs, we can't easily do like auxiliary variables or otherwise because we don't have that joint distributional specification. So I would describe the big picture of missing data, at least for me, teaching you this for the first time, is that it's a really difficult problem to solve. We have some sense of what the problem should look like in a statistical theoretical sense, but from a practical point of view, getting your hands on software to do it is the hardest part. Would you say that's fair? Like we're always like, yeah, but, oh, yeah, but, right, with our analyses. Oh, we did this. Oh, wait, yeah, but we weren't doing that right. Oh, wait, we're not doing that right. So I don't think that there's any sense in the world that, all the missing data problems have been solved. I think the biggest problem is for each type of a model situation that you're in, you may have missing data and you may have a different solution. But these frameworks that I'm trying to tell you work. You have to find a way to implement it is the hard part. Now, a multiple imputation is no different. It gets at some of the problems. It makes things somewhat easy to do. I'm going to tell you that those may be famous last words. Just like me saying, "Oh, we're going to get out early today." We're not getting out early today. Number one. Number two, this is much more straightforward than the other approach. There's a catch at the end. But the reason why it's more straightforward is with multiple imputation, you're creating copy or data sets where the data are complete. And we know what to do with complete data. We just have a lot of the complete data. So we have to combine our complete data analysis. We basically have to do multiple analyses with complete data and combine them. So that, in some respects, makes the best part of the model fixed and more manageable, right? This example I've been running through class where we're predicting these two outcomes. In Bayes, we got to the end and we're like, I don't know what the prediction is because our model is now conditional on all these other variables. All right, that's a problem. We're not going to have a problem here. So, multiple imputation, we're going. A couple housekeeping things. Homework's due this week, Friday. Let me know if you have questions on email or if you have questions in the middle of class, we can talk about them break or otherwise. Next week, I'm not going to assign a reading assessment. In fact, I may not do any more reading assessments the rest of the year. How about that? But we'll do the multi-level multiple imputation chapter next week, and multi-level missing data or multiple imputation. Anyway, multi-level comes next. How many of you have multi-level data? How many of you have psychometric data? Would you say psychometric data is multi-level data? Well, let's see. You have observations nested within a person. Wouldn't you call that a multi-level setup? Yeah. So yes, that applies to you next week as well too. So how many of you have multi-level or psychometric data? See those hands again. Come on now. All right. Enough with that. Let's dive in. So the goal of missing data analysis methods, in maximum likelihood, we saw the goal was to fit a model to observe data and to use the estimates for research questions. And we tried as best we could to do missing data handling behind the scenes. In maximum likelihood, it was easier because we had these, well, in Levon, it was easier because we had these joint distributions we could build and we could correlate auxiliary variables in this big joint distribution, but still leave our model of interest for the variables that we needed to make conditional upon it. We saw that in maximum likelihood sort of deduces parts. Bayesian imputes values themselves. Um, but in this case, the whole method was set up as a means to an end to get those estimates. For multiple imputation, our goal is to create complete data sets and then to use those complete data sets later in analyses, not simultaneous like in Bayes. Bayes is really the only thing that's imputing. Maximum likelihood isn't really imputing. So there's three steps in the multiple imputation process. Number one, impute the data. That makes it sound easy. Yeah, fill in numbers. How do you want to fill in your numbers? We need an imputation model. And therein lies the problem. Every time you heard the word model, in the back of your head, I bet you're thinking, well, if you're like my head, what is my head thinking when I hear model? Every model that we have potentially is wrong. So you have an imputation model. Well, there's a step for being wrong. And if we're building data off of our model, there's our chance for us wrong. So I'll just tell you right now, that first step is sort of an afterthought, especially when we get to mice. Mice has a model built in. Most people just use it, default. Congrats. But you're relying on the right model, right? Or approximate the right model. But then we use an algorithm. Sometimes we call it an MCMC algorithm. It's a little bit different than MCMC. It doesn't always have to be Bayesian, but it's a Markov chain um, that will create multiple copies of the data with different imputed values, each with different imputed values, right? So for the missing data. And along the way, why it's sort of a Markov chain is this algorithm will start with a guess as to what the missing data are, but go on this process where it estimates basically regression model parameters with the data you have, right? And then fills in one of the variables. And then that variable shows up on the next line with others and fills in another variable. So every Markov chain iteration, you'd call it, you end up with a complete data set where each of the missing variables has been imputed differently. Well, that now means that your point estimates for all your regression parameters are going to change potentially. So then you have to go back and re-estimate your regression parameters and repeat the process of filling in data. So that's where this sort of iterative approach or Markov chain comes from. It's a different Markov chain than in Bayesian, because in Bayesian, we often sample the parameters themselves where the data are fixed. Here, we're filling in the data, then sampling parameters, and filling in the data, sampling parameters. Now, the parameters aren't sampled necessarily. By default, they're not sampled in mice, one we'll focus on today. But what is being sampled, what we're basically doing is filling them in with maximum, you could fill them in with maximum likelihood estimates. Now, you could use Bayes. You can always use Bayes. But the parameters of this chained equation approach are not of interest. They're a means to an end. They allow us to approximate the joint distribution of our outcomes, predictors, and auxiliary variables altogether. Right? Now that I said that complicated sentence, I hope you have a chance of parsing it. Joint distribution, meaning all the things all at once. All the outcomes, predictors, and auxiliary, that's the joint. And we're approximating it through a series of basically factored regressions. Right? So these are things that hopefully you've gathered from the class this year. So we have a bunch of data sets. We'll call it capital M data sets. Then what we have to do is for each of those M data sets, do the analysis we actually wanted to do as if the data were complete. Because these are complete data. Just the filled in values are one snippet of what the filled in values should be. Then from each one of those M data sets, we now have M sets of results. Right? So step 2 is analysis. We have 100 data sets, we have 100 results. Now what do? We cherry pick the ones we like best. Okay, maybe not that. We have to pool them together. That's step 3. So we combine the results and we come up with estimates that reflect sort of the overall average of the 100 estimates, standard errors that reflect the variability both um, between and within estimate. And this last process is quite old these days, almost 40 years old, but Don Rubin created it, and somebody started calling it Rubin's rules for how we combine them. It's a fairly common name people use, although it's just kind of weird. It's why does he own them? But yeah, that makes sense. He, I guess, created them. All right. Questions on any of this? That's multiple imputation. Great. No questions. Let's talk about history a little bit. Don Rubin started um, his work in missing data in 1977, wrote a good book in 1987. Really, multiple imputation is a whole bunch of different procedures. And you see in our chapter, we talked about Bayesian estimation routines, although we sort of call it Bayesian. Um, Joint model imputation and fully conditional model specification. And really, the emphasis is on understanding the analyzing imputed data sets and summarizing the results. Um, so again, there are two rounds of modeling in multiple imputation. The first, again, is the imputation model itself. Right. So I'm going to keep talking about, I'm going to repeat myself over and over again. In chained equations, what do we have, right? Let's imagine we have, let's see if I can actually, I did bring a pencil today. Can you believe that? Hooray for me. However, I did not bring my power cord, my power adapter. So got a power brick and we'll see how this goes. But let's imagine we have y, x1, and x2. Those are our three variables, right? Chained equations, a very basic version of chained equations would say the following. We'll set a regression model of y equals beta 0 plus beta 1 plus beta 2 x2 plus error, where error, oh my God, that was terrible. Right, so there's our y model, right? And then, and actually, I'll just put a little y up here to denote each of these parameters for y real quick. And then for x, x1, we're going to do the same type of thing. But now we'll have another beta intercept for x1, a slope for x1, multiplying x2 now, a slope multiplying y, another error. So now y, if we were just looking at this y, this looks like a model that we would use for our analysis, right? But we're now going to create a model for x1 and predict it with x2 and y. This is not a model we can run in the SCM. We can't go into JAG. I guess we could go into Lavon and try to run it, but the problem with this is in a single model that you're trying to run, you cannot take y as an outcome where you're predicting it with x1 and then make y a predictor of x1. Right? We saw last time that the regression coefficient is a substitute for the covariance between a pair of variables. And if you think of y and x1, in this case, x1 and y have a little covariance matrix where there's one covariance only. So this parameter here is taking the place of that covariance. But then similarly, this parameter, the regression slope of y predicting x1, is also doing that. But they're not going to be equal because they're a different metric, right? This is units of y per units of x1. This is units of x1 per units of y, right? So they're sort of inverted. But second, not only that, the other problem with this is that you have two parameters doing the job of one spot in the distribution, which is not identified, right? There's only one that can go there. So this is not an analysis model. This is just the concept is fine between chained equations, okay? Then there's x2, and we're going to do the same thing with it. We'll have a regression line for it. Now, each one of these is going to have error. This would be sigma squared x1. This is y, and then there's error here, right there. So what ends up happening in chained equations is we're building all this because if you think about what we're trying to fill in, if each of these were continuous, let's just start with the multivariate normal distribution, we would be looking for this covariance matrix of y, so y, x1, x2, y, x1, x2, right? This is what we're sort of trying to fill in. The line up here for y checks off these two values with the two slopes. It also checks off that value with the residual variance. They're rescaled, but it works. Those are the parameters where it comes from, right? The line for x1 does the same thing. We have directly in the model the x2 slope and the y slope, and the residual variance should check off the other. And then finally, for x2, the same thing happens. We have x1 and y, and then the residual variance should check off the variance for it. So the chained equations is trying to get about if we could come up with a solution to try to get a covariance matrix for all of our variables at once by which we could impute our data. How are we doing so far? Okay. But how does it work? Because we can't do this simultaneously. So it works like this. Step one, we fit this regression line right here for y. We all know how to do that. We could do it in LM, right? Step two, we take our parameter estimates and a residual variance, and we come up with a prediction interval for y. Now, remember in basic regression, there was sort of different intervals for prediction, right? We want to predict one person's y, each person who's missing on y with a value based on their x1 and x2 values, right? So y will come up with a y hat for a person, which the mean of that y hat, it'll follow a normal distribution here. The mean of it will be the regression line. But we can't just impute with the mean, because the mean of it will cause us to have less error in our imputation than otherwise would be there. So instead, what we do is we impute it with the variance of prediction, and that's a formula that I don't even I remember, but vaguely. Long story short, we can plug in that variance, calculate what it happens to be, and plug in each. Now, so what that means is for y, now we have a set of random values loosely associated with the model, but having error to them. So far, so good? Any questions? So now we have complete y, or new data for y. We go to the next step, and we do the same thing for x1. Number one, estimate the regression model. Number two, for all missing values, sample x1, conditional on their value of y. Now that y may have been imputed in the first step, or it may have been observed, right? So we now plug in x1 with the same idea, but with the same prediction error, same standard deviation that's equal to the standard error of prediction that we have for it. And then finally, we do the same thing for x2 and plug it in. That is one iteration. And why I call this a Markov process is it shares a lot of similarities to the Markov chain that we saw in MCMC. In that, here, y, x1, and x2 are like our sampled parameters, and we're updating them throughout one iteration. Basically, every value that's missing has a chance, or this is not rejection, it's just sampling, it's like Gibbs sampling, changes its value for every time we do a data set. But here's the problem. When we have missing data, we know when we start, our regression parameters are not going to be really accurate yet, because they may have bias in them from missing data, right? For this first line, if we're having missing x or on x1 or missing on x2, all the betas may be biased. Same with the standard error of prediction. So we can't just do this once. This process has to continue multiple times. It's just like a Markov chain, right? And so this process of sampling at every iteration, once in a while, we will stop, grab a data set from it, and use that data set. Right? But as this process goes, you can imagine what's going to happen. We can almost use the same theorem under Markov chain Monte Carlo to understand that as we go along, each of our betas should start to move toward the distribution that they should look like if they were there, meaning we are eventually converged to something that's sampling from the joint distribution overall. How are we doing with that? So literally, if you're good with regression, you could build that algorithm on your own. And I'll show it to you in class a little bit, but we'll do mice afterwards. But that's the imputation part. And I'll just dive in my slides, but that's probably over just jumped over everything I was going to say, but felt like that'd be easier just to draw. Yeah. Yes. Yeah. Yeah. Pardon me? Oh, no, the first one, we may just plug in random values for anything missing overall. That's right. Mhm. That's right. Now, they're not just predicted values, they're predicted with error, right? So they come from a prediction distribution, not just the regression line, but yes. Mhm. That's right. Correct. That's right. That's right. If we were to do this in a joint model, where we put, like, if we specify this model in Lavon, it may converge. It's most likely to have ridiculous standard errors and probably won't converge in the first place. That's right. That's right. That is what we're after. This is what we'd like to have, but we don't have it, right? We don't know what this is. And the joint model itself is not going to tell us what it is without having error to it. So we use this process to sort of approximate what this, if we knew what this truly was, we wouldn't need this whole process, but we'll never know what this truly is. But each of the corresponding parameters in this process fills in a different portion of this same covariance matrix, is what I'm trying to say. That's right. Mhm. Other, yes, again. Yeah, so the difference this process in JAGs is that in JAGs we had to factor our regression, but we also couldn't build this simultaneous model, right? Um, number one, in JAGs has a problem whenever you take something with Y and, well, you might be able to put things here. JAGs has some weird, interesting things what you can and can't do with variables. But more importantly, once you have in JAGs, we could basically work with the lower triangle of this matrix. That would be done by taking, maybe an empty model for x2, right? So here, x2 equals beta 0, x2 plus error. And that would then take off this value, and then x1 would be equal to, and you see where I'm going with this. Basically, we're filling in only the lower triangle and the diagonal of the matrix because that information is what we would use to um, determine the rest of the matrix. We can't do it all at once. Did that help? Okay. Other questions? Yeah, doesn't exist. That one. So yeah, if we have this sense and one of these is not normal, this evidently I have it on. This thing goes out the window because there is no easy to specify joint distribution between a binary variable and a continuous variable, right? You sort of have to condition it, right? You have to say, what's the distribution of the binary variable, and then condition on that, what's the distribution of the continuous, right? So the difference is here when we if let's imagine that y is continuous and x is binary, right here, right? We still want the x and y distribution. That joint distribution is important to us because without it, we're going to be sampling things that are approximating it, right? We need that to tell us the full joint distribution of our data. but we can't get it. This doesn't exist. But we know through statistics that this is really equivalent to the following, right? So this is where the term factored regression comes from, but our whole covariance matrix here is out the window. The reason why it's out the window is that there's no, for one binary variable, this is pretty straightforward, and this is an exact approximation. If we have more than one binary variable, we start getting into issues with what do distributions moments look like? Moments meaning their parameters, right? In a multivariate normal distribution, we're actually protected. We only have two sets of parameters. As complicated as it is, right? With the ugly likelihood function, it's two sets of parameters. There's means, which is univariate ideas, an idea, a parameter that describes one variable, and there's covariances. And a covariance involves a pair of variables unless that pair is the variable with itself, and that's the diagonal, right? It's the variance, right? So if you think of the types of parameters we have parameters that involve one variable at a time. We have parameters that involve two variables at a time. Those different types of parameters in statistics, you can talk about them as central moments of the distribution, first moment, the second moment, and so forth. Well, when you start mixing, it turns out multivariate normal, there is no other moments of the distribution that aren't parameterized. Meaning, a third central moment is often something we talk about as skewness in multivariate normal. Skewness as a constant. It's always fixed because the multivariate normal is symmetric. It's not skewed. So there. We also talk about kurtosis. That would be the fourth one, right? In a multivariate normal. Well, it turns out that's also fixed. So there's no parameters there. When we switch from multivariate normal to some other distribution, though, those moments, maybe not the same names, but the same idea, uh, location, spread, skew, kurtosis, etc., those ideas hold, but now we have parameters that take the place of it. Like those are quantities we have to estimate. And so when we get to more than one binary variable, we may not exactly approximate this either. That's toward the end of the chapter where they talk about conforming distributions, something along those lines. So our problem is when we mix and match variable types, which happens all the time in research. That's what analysis of variance was taught as. X is discrete, Y is continuous, right? Very simple. One-way ANOVA, your first one-way ANOVA. When did you run that? Some of you may have been in high school when you ran it, right? Not me. Don't worry about it. I didn't spend much time in high school. I mean, I was there 4 years, but I didn't go a whole lot, right? The idea was really, once you think of it from the concept of joint distributions, a multivariate joint distribution with mixed type variables is nearly impossible to directly estimate. You sort of have to go case by case to derive what those things were. Nobody has the time for that. Nobody has the time for missing data in general. Don't get me wrong, but especially trying to derive it. Does that help? I feel like I'm on a tangent. Am I on a tangent? Probably. Whatever. I'm I'm so like feeling stressed these days. I'm not a tangent, whatever. I can't even worry about that. But so what I want to get at is imputation model is a model, but it's not an identified joint model. The imputation model here would be considered our three ways that we're filling in data for y, x1, and x2. Okay? Yeah. The same as you would specify in a normal linear model. But you just have to think about the prior distributions being now specified. Each one of these is a separate model. So each of these may have a separate set of priors, but it'd be the same, right? So basically you could do the same process, right? Where I said, oh, estimate the parameters. Well, I was saying use like LM to do it. Well, you could use JAGs to do it, right? The same thing happens. You just then with the parameters, you can point estimate of Y, right? So yes. Does that help? Okay, so this is the imputation model. What you don't see here are anything curvilinear between X and Y. You don't see interaction effects. You don't see any of that. It's just our basic, simple imputation model. And this is the default. It's a good place to start. Just putting that in your mind now to realize that even though imputation is going to be way easier, let's just put it this way, it's going to be way easier than JAGs and probably a little bit easier than Lavon in some cases. All right. In fact, it will be better than Lavon in some cases as well. Actually, we're going to combine this with Lavon, but the complete data version of it for Lavon is much easier. Um, but we still rely on assumptions. That doesn't get us out of the way of assumptions, right? And remember, when you say model, that's a huge assumption. Cool? Okay. All right. The analysis model, this is the model of interest, right? So this imputation model is what you do first, and it may not be the model of interest, or it may be. The book chapter describes the agnostic approach and the model-based approach, right? The agnostic approach basically says, throw everything in this. Make a model that's more extreme than your model, and then estimate your model, because your model is subsumed in the extreme model, right? The extreme model subsumes your model, excuse me. The model-based approach says, actually, I'm going to go and use a model more specific to my needs for X and Y and so forth. Problem with the agnostic approach is there's a ton of parameters. The problem with the model-based approach is if now you're sampling or imputing based on the same model that you're using, you're making a heck of an assumption about that missing data, and it's likely to confirm that your model is working really, really well if you have a lot of missing data, because the missing data tend to look like your model then, right? So why he talks about both in the part is because, again, we're in this world where there's nothing but roadblocks with missing data. That's why I say don't ever have missing data. Problem solved. Clearly, that's easy. But one of the roadblocks here is that you may have a model specification that doesn't work well with this. He mentions having curvilinear interaction effects. I don't know entirely if that's, I fully am on board with it. I think it's more complicated than how it's mentioned in the book. But you may have to go and use an imputation model that looks like your model, because your model is complex enough that we don't even know what the other one would be. So it's sort of the fallback. But to me, my approach is always do the least amount of harm. The agnostic model is my favorite, because the agnostic model, if you build that joint distribution correctly, then it should resemble more than just your model. It should have nuances of the data implied with it, which will make for better, more accurate results. May not be very, like, your standard errors may be wider, but in terms of falling on the side of like a conservative approach to science, I think the agnostic fits into that more. But now I just talked about more than I need to. Anyway, the analysis model, that's the second part, right? And we're going to use the same example we've been running with predict performance and use. Turns out the very, very first set of Lavon syntax is our last syntax today, the simplest one, because we have complete data, right? It's just we have to go through this imputation process to get to it. But that last model will not look like this, because we're using an agnostic approach to it, right? So we have to separate where the models happen to be. That's the key catch here, right? It's kind of funny, right? Why would you need all that to impute your data? Because data imputation, you have no idea what the data should be. So you go with, I got all this data. Let's use it to figure out what the data might be. And then I'll go specify my model later. And there's always a mismatch, potentially a mismatch between the two. All right. But once you've then fit your data, you have the cool data afterwards. So I just mentioned agnostic imputation. Again, the goal is to apply a flexible or non-restrictive model not dedicated to one specific analysis. So you want to build this in a way that doesn't just generate data that confirms your model, right? Those imputed data sets could be used for multiple analyses. You could have nested models. You could do your model exploration process. Garden of forking paths, some people would say, but there is a model building process, right? Particularly, you've seen it. I know Lisa's classes pretty well, even though I haven't sat in them. I tend to know what she's talking about. But the model building process, like when you get through empty model, if you're in multi-level and random intercepts, et cetera, you can do all of that with all the multiple imputation. You don't have to re-impute every time that you get a new model. You can just take your pooled amputated data sets. That's where we take data out, right? Amputation versus imputation. Huh. There's some one of you can use that. Workshop that for me. Let me know how I can make that a joke. Yeah. If you have if you can do it where you have one imputation, that's the best way forward. One imputation round. So you create 100 imputed data sets with a very, to me, the ideal is the agnostic model, and then every other analysis in your paper rely on those 100 data sets. Does that make sense? Yeah. So the important here in the imputation model is flexible enough to preserve the important features of that secondary analysis. What are the important features? Again, you're not just generating data from the analysis model itself. Model-based imputation is where you impute with the same focal analysis model itself. Um, this is much more narrow in scope, but it's there, I think, in case you don't know how to do the bigger picture, try this. This at least is better than doing nothing. Okay? So which one do you use? I just mentioned that as well, too. So, all right, how we doing? Okay. You see I have 84 slides, so I'm moving a little bit quicker today. Okay, so the idea between joint model imputation is the idea is we're deriving the idea that we're taking this multivariate distribution approach. We want the joint model, the big model, to impute our data, because the big joint model, as I wrote on my iPad here, is the one that has the most generality for what we're doing. Joe Schaefer was important in this, and most of the early work was on multivariate normal and multinomial, because those are very common distributions. Multinomial being a multi-category discrete variable, right? Um, Now, the book and I differ on the latent response formulation, which chapter 6, where we talked about the Gibbs sampling with data augmentation. Remember that? I showed you the paper last week. The book likes to say that they always use latent response formulations. I disagree with that. And Plus uses it. Limited information folks do it, but the rest of the world tends to not. They just use regular data. There's nothing about, if I go back to my handwritten notes here, and if, for instance, x1 is really some type of link function, we apply some type of link function to the data, there's nothing about that that's wrong. Just not a latent response format. No big deal, right? Here in this case, the corresponding latent response would be the part that's submitted to the link function anyway. So it's an odd formulation, but really our modern approach, as you see, I think largely relies upon what's capable with easy to use software versus what's something you have to build yourself. Most people don't have the training or the patience to do that, the software. And I get that. You're studying your field. You're studying the thing you want to build, right? You want to estimate, you want to understand it. Where are you going to build software? Plus, building software takes so many more months onto a project. Those of you who've worked with me, if you come up with a model, be like, oh, do you want to add another year and a half to your dissertation? Because that's what it'll take, right? Case in point, one of my students from many years ago, she was going to use M plus for something, and I made a comment in her dissertation proposal. I'm like, actually, that's kind of a problem. So, well, I'll just estimate it. Yep, a year and a half later, right? It happens. So, yeah, how many of you are going to create software for this for a data analysis? Probably not. If it's your line of research, absolutely. Cool. But if you're like me, this isn't my core part of research, and the part of research I care about, I may. But if someone comes to me and wants me to consult with them on a missing data problem, I'm going to try to not build software for it, because otherwise, I already have a day job. Actually have a small business. I don't have any more time after that, right? Like to see my child before he turns 18 once in a while, right? That type of thing. Spouse, child, family, that sleep, those things. So let's give an example here. This is an example from his book, Math Achievement Data. You've got pre-test and post-test scores plus some other academic variables. There were 250 people. The pre-test was complete, but the post-test had missing data. And what you're really after is this change score, which is the pretest or the post-test minus the pretest, right? So we could go and create an analysis model where the change is just an empty model, but this mean is the mean difference in change, right? So that would be kind of important. Uh, so the benefit of incorporating auxiliary variables is that multiple imputation will readily accommodate these auxiliary variables um, automatically if you build the imputation model to have the chained equations with auxiliary variables in it, right? So here you've got standardized reading scores that have missing data and standardized free and reduced lunch variables that also have missing data. The purpose of these are, though, not predicting missingness directly here. They improve the power by explaining potentially variance in test score, right? So the joint model specification is where we may have each one of these four variables. And for the sake of this example from the book, I've left Y4 in this latent response format. So we can say if we had the latent underlying variable for Y4, like from our example from last week, all four of these would follow a multivariate normal distribution with some covariance matrix and some mean vector for each, right? And here's an example from his book. This Y4, this little tilde here is this is the continuous underlying response. And then we have to transform that into the actual discrete free and reduced lunch variable, an indicator of whether a person gets free or reduced lunch. Um, so this imputation model is considered agnostic because what we end up doing here is we're imputing with our joint model, potentially. Like the first part of the chapter says, can we come up with this covariance matrix rather than using chained equations? And this joint, really what we're after is the difference between y1 and y2. But we've got these auxiliary variables. So the joint model is bigger than our model of interest, right? Does that make sense? So it's agnostic. Um, so there we go. Questions on any of this? Am I going too fast? Okay. So we can do missing data imputation in joint models as well. And what we would have to do is we'd have to impute the multivariate, well, imputing multivariate normal data involves converting estimated parameters, in this case, the mean vector and the covariance matrix, into a series of regression models. And that is the process that I was talking about with chained equations, right? A specific regression model gets derived for each of the each unique missing data pattern. Oh, this is, pardon me, this is the joint approach. So each missing data pattern may have its own regression approach, and MCMC is used for it. And in this case, again, this is, I didn't do a good job in my slides differentiating this. This is if you have the joint model itself and didn't do the chained equations. This is like the big approach, not the otherwise. But basically, the idea is that we could go and we have a set of patterns of missing data. We have four variables. So there's 2 to the 4 possible patterns of how data can be missing. One of those where they're all missing is something we'd throw out altogether. So there's 15 instead of 16. 15 different patterns of missing data. We would try to estimate our mean vector and covariance matrix, sorry, a different regression model for each of those, and use that to generate our missing data. And in this case, we have one for Y2. We may have a different one for Y2 and Y4 as we go forward. That each of those would be used to impute the data that follow that missing data pattern. And the pattern is used here because this is effectively trying to, this process of doing the joint model depends, we're basically saying there may be a different set of parameters for each type of pattern. It's kind of a mess though. And we could do the same thing with imputing data. But anyway, same with categorical data. Now we can save filled in data sets for each iteration. Actually, let me stop here and compose myself right here. All right. So with this process here, where we're filling in each of the data that are missing based on a different pattern. The same thing can happen. We could fill in our data with all the patterns, take the data set that we have, save it, and do the same process over and over again. Let's see here. But the problem is, especially with any of this work that we have, is that the same problem in Bayesian analysis that I was saying, for a lot of our parameters, it's not a big deal. Autocorrelation, point to you because you asked about it. The autocorrelation is a problem in missing data. Because if we're doing these sequential data sets and data set one looks a lot like data set two, that could be a big problem in our secondary analysis of them, the analysis phase. Because if we just take the first 20, those missing values may be so related that they're not really 20 samples of what the missing value should be. So instead, what we may end up doing is the same process that we did in MCMC. What was the thing we had to set if we didn't want we wanted to lower our autocorrelation? Do you remember the parameter in JAGs? I don't think I talked about it much, but it's called the thinning interval, right? We want to thin the chain. Here, our Markov chain, if you will, is a set of data sets. And instead of taking the first, if we want 20, instead of taking the first 20, we might just take 20 data sets, but take every 10th data set in the chain, right? So 10, 20, 30, right? So that would be, we need to generate 200 data sets just to get 20 that we're going to use for our analysis. So that's where thinning is. We could do the same thing with parallel chains. And this is the same process that we saw in a Markov chain, Monte Carlo. Remember in Markov chain in Monte Carlo, I like to run 4 parallel chains. And within each chain, I could calculate autocorrelation. But then I pool the chains together. And from those pooled chains, I could just randomly permute the order and draw them at random from the pooled chain. That's the difference between sequential or parallel, right? Parallel meaning starting separately, running in parallel, and so forth. All of our, by the way, a lot of the interesting stuff that you see, a lot of the preliminary work in missing data, if you're reading the methods literature in the late 80s, I was alive then, many of you weren't. Let me tell you about computing it back in the day, right? The Nintendo, the original Nintendo. I mean, how many, you couldn't save your games on it, right? Because it didn't have any space for it. So a lot of things that you see, like 20 data sets, or better yet, 5, is based on the computing power of the 1980s. We got lots of power these days. We don't need 20. We do 2,000 or 3,000. At some point, it's overkill. But when you see an arbitrary number like 5 data sets, remember that sort of started back when computers looked a little bit different, right? Similar to what we did before, we may have to check for convergence. In this case, it's convergence of our model parameters as well too. And so I just mentioned how many imputations we might need. We may need, back in the day, 5 was talked about. How many imputated data sets are necessary for the analysis phase? Back in the day, 3 to 5. That's 1980s technology. Remember, you may not have been alive when Nintendo came out. I was. It's pretty amazing, especially the Duck Hunt game. But remember the cartridge you had to blow in, right? That's 3 to 5. That's do you know what I'm talking about? Like, you ever played Nintendo? Like, it had this little plastic thing you had to put in. If you played too much, it would get hot and it would quit running. I know this because I did that with my friends a lot. So you took it out, and what did you do? You blew on it. Because that's what you do with everything, right? I mean, it's blow it, cool it off, right? That's the 3 to 5. That's the original Nintendo system, or Atari before that, the Atari 2600. I don't know if you remember those. That thing. Now, I'm not as old as to say I was an old man when that happened. I was still very much a child. But yeah, 3 to 5. Now, 20 to 100 people are saying. I think probably like anything else in statistics, it all depends on how complicated your final analysis model is. If you have a very large multivariate model, a lot more data sets will probably be needed. But it's very easy to amass thousands of data sets, even for complicated models. The other picture of this is why you have so many data sets is because you're trying to reduce the error in sampling as well too, right? Random sampling process. We call that Monte Carlo error. using too few imputations itself can introduce this noise in sampling. Right? If you there's regressions from, for instance, if we were talking about chained equations, the values that we're imputing for y may have a lot of noise to them, right? So to summarize that noise well, if we just use two, and let's imagine y is sampled from a number line like where my arms are, but by chance you just happen to get the two on this side of the number line, it's Monte Carlo error, right? So the longer the error, the more the error potentially, the bigger number of things you need. So practical recommendation, people say 100 at least. Craig uses 100 in his text. So why not pick 100 or more? All right. I know it's break time. How about we take a break? I'm going to go see if I have a power brick upstairs, try to calm that part of my life down. And I'll come back in 10 minutes, a little bit after 1:30, pick up where we started. All right? All right. So, in summary, the joint model imputation, which starts the chapter, I think is less relevant to you and less practical. So, I'm sort of skipping over it a little bit quickly. If you don't understand it, don't worry about it. Just don't do it. If you want to understand it, let me know. Come talk to me. We'll handle it. Okay? There. Next, let's talk about the fully conditional specification. It's also known as chained equations. MICE stands for multiple imputation through chained equations. And that's the process I laid out for you at the beginning of class. Um, so instead of working with this multivariate normal distribution like in the joint model approach, this fully conditional specification specifies our model as we had drawn out, or I had drawn out, and it's not even on here anymore, on my iPad previous to this. So you're not going to see that. I can hold it up for you. Almost dropped it. That would have been lovely. Okay, so we talked about the logic before that. The nice thing about that is when you have a, a variable that's not necessarily multivariate normal or doesn't fit in this latent regression style approach, you can use chained equations and specify distributions that fit your variables. How many of you have count data? Good. Don't have count data. Don't have missing data. Don't have count. Why do I say don't have count data? How many distributions are there for count data? There's Poisson. There's negative binomial. There's the zero inflated versions of Poisson and negative binomial. There may even be hurdle versions of that as well too. But in the chained equations approach, which I can't show you, um, that approach allows you to just specify a univariate model as you would otherwise. So, how many of you took the generalized class with Lisa? Right? It was a model soup in that class. Would you call it? There's a lot of models, right? And it was always like, here's the type of data and all these other models, right? Well, all of those models were univariate. I guess you got the path models, except for the path models. Everything else was univariate. That fits because each one of those lines in the regression could be used to impute data. So chained equations could really be something that is flexible enough. And actually, to me, chained equations is the place what you should start. It's last in this lecture because you sort of build up concepts to get there didactically, like why multivariate normal? We talk about likelihoods. Why Bayesian? Well, we have likelihoods, and now we have imputed values. Why chained equations? Because we sort of shortcut both of those and get imputed values, right? So I think didactically, the book is written this way. But from a practical point of view, my recommendation is you go to chained equations first if you can. And if can't, go a step further. Then think about it. But again, the chained equation mechanism, the book describes it as a round robin scheme, which is like a sports term. What really means is each variable gets predicted by every other variable. Okay? The steps I laid out before, but basically for an incomplete variable y, specify a regression model predicting y from all the other variables and cycle through each incomplete variable, imputing its values based on the current values of other variables, right? So y itself would have some type of density function. It would be a function of, so how we read this here, the current value that we're trying to impute, or the current model for that variable we're trying to impute, comes from is a function of all the things that were sampled this iteration, right? So and all the things that hadn't have yet to be sampled yet in this iteration. So think of it this way: if this were x1 on my y x1 x2 slides, which again I should work harder to see if this will work. Yeah, not there. Oh well. All right. In y, in basically, if you're thinking this is x1, well, we imputed y in this one step before, so that's why t is the current iteration. So y got imputed, x1's being imputed, but x2 hasn't been imputed yet. This time it was imputed on the last iteration. That's how you read this notation. Does that make sense? And here you're basically describing it as a series of incomplete, maybe some complete variables. And this phi term is the whole generic placeholder for all the parameters for each of these models, this model itself, right? So if you're predicting y vi, the predictors are all these terms here. Each one of these will have a regression coefficient attached to it. You may have a residual variance and so forth. All those parameters go into that phi term. That's how you unpack this notation for what you do. Um, So chained equations is like a Bayesian framework for imputing your data. It's not necessarily Bayesian. I sort of differ with the book on that. Like you can do the same approach using frequentist statistics, right? The idea of chain, though, gets conflated, right? Because we say in Bayesian, we show Jags does Markov chain Monte Carlo. We're doing Markov chains here, but each chain itself can consist of non-Bayesian values. Right? And I'm going to show that in just a bit here. Right? So this is the example in those four variables in Craig's book. Math pretest, math post-test, standardized reading, and free and reduced lunch. And here, if we were to remember, he had the pretest that had complete data. So that's not actually part of the imputation in terms of we don't need to impute variables for it. So the set of chained equations would be math post, standardized reading, and free and reduced lunch. But just because the pretest doesn't have any missing data doesn't mean we don't include it in the chained equations, right? So if we have complete data, those complete data go into our chained equations too as part of the prediction model for each variable. They're just omitted from the step where we'd have to impute for them, right? Because there's nothing to impute there, right? So we're not going to replace data with this that we have. So now the same type of thing. Here we would impute math post based on its prediction method function, standardized reading based on it, and free and reduced lunch based on it. Here, would you like to see this in practice with some data, some code? So my R script, I see you squinting. I'm sorry about that. Is that better? Okay. Can you see that or do you need bigger? A little bigger? Okay. There we go. The in-person class is great, except for when you want to see code, right? And then online seems to be a little bit better. But I personally like in person better because I can see your faces. But at the same time, I like online quite a bit too. Anyway, I don't know where to go with this. I'm not going to fight this battle now, though. But this is what you have at the beginning of my file here. Make sure what I just saw. Yep, that works. This is the same data that I created weeks ago to do our analysis with. So that top part is all of that. And now I've tried to notate what I have in my file here with, we have 213 rows of missing data, basically. So now what we're going to do is we're going to pretend that we're mice in this setup. Right? We're going to build a mice-like algorithm, an imputation, a chained equation algorithm. And I'm going to start with my data to impute. And I'm going to start by imputing the values of each of the variables, in this case, with just simple constant values to begin with. Now, you tell me, what's the problem with this? This is single imputation. Not only that, except for female, for each of these other ones, we're doing mean imputation. What's wrong with that? That's bad if we fill in one data set with it. But in our process, it's not as bad because this isn't the data set we're going to use. This is the starter data set. And we need to have values in it somewhere. And just like in Markov chain Monte Carlo for Bayesian estimation, the starting values of parameters literally could be anything. And if you run the chain long enough, the chain will find its way to where it needs to go. The same thing happens here. So we're going to start with something relatively easy by plugging in for each variable that's missing. The female variable is binary, so we just put in the mode. That means everybody gets a 1 who's missing to begin with. And for the continuous variables, we're going to put in the mean. So now we have our data frame. It's complete, but you'll see a lot of the missing values are the same. Like here, where I can tell you that these were missing data set points right here because they're all the same value, right? And then they're multiple cells. So the mean of CC10 was negative 0.35, I'm guessing. And let's find out. Well, I've lost it now, but there it is. Yeah, there's the mean. Actually, it will be the mean if we imputed with the mean. It doesn't change anything. So we just created a complete data set, not a good one, but something to get us started. I set a random seed. I figure out which variables I need to impute. So for each variable, these are the values I need to fill in right here. Right. By the way, I'm not describing my syntax here, which is really dense. I'm doing it for showing you how the process works. Right? I don't expect you to go and create your own mice syntax. I expect you to use the mice package. Okay? That syntax I'll describe a little bit more once we get to it. Okay? So here we also have, oops, typo immediately. These are the variables we need to impute, right? So basically the first 2 lines, these lines right here are telling me, do I have complete data? No, I don't. I have missing data on all my variables. So this is my version of the mice loop right here. And I'm going to start the iteration at 1 and walk through what an iteration looks like. I'm going to set the variable equal to 1 and start with the first variable. So here are our predictors. The formula that I have is the following. So now, here is where we get into this. The other part was setting it up. So basically, what I first need to do, this first variable is, actually I need, our first variable is performance. So let's go to the imputation for it. Hang on, let's see here. Did not do this correctly. So the formula for performance is the following. Predicting performance with usefulness, CC10, and female. Okay? That's us doing a linear regression as if everything was complete, because we have complete, if not bad, data right now. So we estimate that, and you can see these are our regression coefficients. These are meaningless to us. We don't want to save those. They're not important. What's important is what we do with them. Next, we can go and predict the values of the predicted means. Here, I'm actually just using the residual standard error to impute. This is our standard error. In fact, if I do the summary, you will see our residual standard error is 2.729 on 266 degrees of freedom. So now what I've done is I go to the imputed values, these are the values I need to impute. And here I impute them with a normal distribution where the mean is set to the predicted value for each person, and the residual standard deviation is the residual standard error. And now I have a bunch of new imputed values. Now these values will not be identical. So even for the people who have the mean, the only way that these would be identical, I guess, is if they were missing on female, CC10, and usefulness, and they all got the mean imputed. But that's going to change really quickly. Okay? How are we doing? Okay? So next, we come along We plug that into our original data, and we go to our next variable. Where is that? Right up here. And our next variable, our formula, is the following. It's usefulness. You'll see performance, which we just imputed, is here. So that would be the current value that we imputed. But CC10 and female were the original values from before. So again, we go through our process of setting up our data. And now, again, it's performance. We estimate our model. There's our model coefficients. And then at the end of that, we get our predicted means. And we go and grab some more imputed values. You get the point? Over and over and over again. Now, I will say when we get to female, is that variable 3? Let's take a look. Let's imagine I skip ahead to 4. When we get to female, though, now female is a binary variable, and we can, instead of using LM, we can use GLM, because this will allow us to do a logistic regression. Right? Now, it's not a logistic regression. This is not like the factored regression of female. Remember, in the maximum likelihood with SCM approach, I put female into the likelihood by itself, predicting it with an empty model. That's not what we're doing here in the chained equation. We're trying to do the best job we can at figuring out what female might be based on all the data we have apart from it. So in this case, we go to female. We estimate a logistic regression. So now logistic regression is a little bit more interesting because the logistic regression doesn't have a residual error. And these values are in logits, right? So these are not predicted values of y. This is for the predicted value of the log odds of a correct response for y, right? And so that's okay, because what we end up doing is we can create predicted probabilities using the predict function as well. That's the probability each missing data, or all the data, actually, for each piece of missing data here, that's their probability that that person was originally a female, right? This is keeping probabilities within bounds because we can use the R binom function to generate data. And now when we do that, our values are between 0 and 1. By the way, this step here is making sure the probabilities are sufficiently far away from 1 or 0, because if you try to predict a value with 1 or 0, that function sometimes blows up. It may not blow up, but I know the log version of it does, so we don't want to mess with it. So there we have it, right? So this process is nice because we can understand how our data are being imputed. It's just multiple of univariate models with all the variables predicting everything else. We can run this a whole series of times, and take a look at what happens to our coefficients as I do this, right? So I'm outputting, evidently I'm not showing the outputted values. There we go. Pardon my mistake in my code. I wanted to show also what's happening with this as we're going forward, right? Not only are we imputing the missing data, well, I don't see female there, but take a look at the coefficients for the others, right? The other coefficients are wiggling around as we do this. And that's because every time we do a different model, the missing data of the other predictors has now changed, right? And so what we want to do is run this process long enough so that we get further and further away. You can think about each time we go and generate a complete data set, it may be the missing values may be highly related to the one from the previous iteration, that autocorrelation. This is sort of tracking how numbers are changing over time, or if they're changing at all, there's the fluctuation. But the missing values themselves are moving away from where we originally imputed them to be. So I think this type of version is showing you that sort of what's happening at each step of the way. We're estimating our parameters over again, trying to impute our data as best we can. So we're getting better parameter estimates for each model, right? In theory, this process is sort of moving our missing values closer to where they should be, but simultaneously moving our regression coefficients, trying to remove the bias of missing data from those as well. right? Because any given regression model right here is relying upon the imputed data. And this imputed data that we have, if we specify this correctly, will allow us to assume missing at random once we get through the whole process. It's just this process had to start somewhere. That somewhere that we started is not good. It just takes a while for it to get there. Maybe not that long. It's may even be close to where it is now. It's 4 variables. How are we doing with all this? Is this interesting at all to you? All right, let's see here. This is giving you the last imputation value as well. So that's the process that goes on in multiple imputation with chained equations. And we're going to see the mice package makes this very nice, very easy. But I want to get through a couple other features here, right? There we go. I don't know why all of my notation is now repeated. It wasn't before. That's fun. Try one other time here. All right. So the other thing that we have to think about that the author brings up, Greg brings up, is that the question is whether or not our regression, this set of chained equations, are compatible with the full joint distributions, compatibility argument. And this is what I was getting at when I mentioned before. When we start mixing the types of data, we get into joint distributions that you can't easily specify with this set of chained equations, right? You may have missing moments or missing parameters that they're not approximating. If everything's continuous and use multivariate normal, it's compatible. If you have one binary variable, it's usually compatible. It's compatible. So when you start to move to like 2 or more binary variables and so forth, it starts to become less and less and less compatible. And the question is, how close is your series of equations to that joint model that you're really ideally specify? And Craig indicates that it's actually pretty close. So we don't really have to worry about it. So most of the time, compatibility, at least in the work I've seen, is like, yeah, I know this is more complicated than this, but I need to get this done. So it's close. It ignores it. So don't need to go into that. Don't need to go much more in that. But basically, the idea then is this process that we're doing here, we can save the filled in data sets at any given iteration. I just had 10 iterations. I could have taken, if I wanted to take every fifth data set, I could have 2 data sets I'd pull out of that, right? That would be that wouldn't be sufficient for doing all my analyses, but you can see what we're doing, right? At the end of every one of these loops, our missing data, our data set is complete. So we just take that data set as if it were the complete data and hold on to it. That's our imputation phase. How we doing? Questions? All right. So now, once we have every data set, I mentioned before, we have to estimate our model on all those data sets. And then what do we do with the parameter estimates? That phase. So I skipped over step 2 on this set, but we get straight to step 3, the pooling parameter estimates. Turns out when we pool those parameter estimates, if you think about it, our final model that we're after here is predicting performance using CC10 and female, and predicting usefulness with CC10 and female, right? So if we had 100 data sets, we'd have 100 estimates of the slope of performance, of CC10 predicting performance. Let's just take that to focus on it, right? How would we summarize the actual slope from that 100 estimates? Well, it turns out in this case, it's the average slope across all the estimates. So your point estimates for your model parameters will come from a simple process of summarizing, averaging, right? Here's your model slope, the average for it. That's the easiest it gets. I like that. Here, our assumption is that each of the estimates themselves follow somewhat of a normal, approximately normal sampling distribution. That's why we can summarize it with a mean and not some other statistic. It generally holds well for any type of mean in your model, a regression coefficient, proportions. Maybe it doesn't work so well for correlation coefficients. And then, of course, we saw in Bayesian, the sampling distributions of variances and standard deviations may be somewhat skewed. So if we take the mean of it, remember taking the mean, the EAP estimate in Bayes, it might move the mean toward the tail, making it look somewhat inflated. We also have R squared, anything that involves statistics that we do as well. They may not be as easy to average. So instead, there are ways that you can talk about this. You can convert them to something that's average. So if you get into a situation you really want to go and look at correlations, um, remember, I'm guessing intermediate taught you the Fisher's R to Z transformation. You ever heard of that before for correlations? You may not have. That's okay. It's a very classic way of taking a correlation coefficient, converting it to a z-score, and then using a p-value on that z-score. And that's effectively what you could do here too. There's a lot of people that would end up being able to do this. If you're in that spot, send me a note. I can help you figure out how to summarize if need be. Turns out, for a lot of the models you do, software may pool it for you. So what I'm going to show you later on after this is something called the Levon.mi package, which is a derivative of the SCM tools package. And it will do the pooling for you. So a lot of these formulas you go to when you're in need, but you may not be in need. Okay? Someone may have taken pity on us. And I say us because I don't want to do this if I don't have to, right? All right. What you don't want to pool by averaging are test statistics or p-values, right? So ignore that. This goes. Okay? Okay. To pool standard errors, that's averaging standard errors is not necessarily correct. The reason for that is each standard error is calculated from a complete data set, treating the imputed values if they were the real values, but it underestimates how much uncertainty there's introduced to the imputation process itself, right? So you think of it this way. If we have 100 data sets, we have 100 analyses. Each analysis itself, for every parameter, there's a standard error. That's a within analysis standard error. And then if we looked at the 100 analyses, the parameter of interest, and calculated the standard deviation of that, that's like a between imputation standard error. Those two sources of error have to be combined to give you a standard error that's appropriate for your imputed data. So with that, again, we can calculate within imputation variance, that's the squared standard error for each, and the between imputation variance, that's the variance across each of the values of the parameter itself. Right? That's what I'm talking about here. Within imputation is the sum of squared imputations over. It's basically the average squared standard error across those 100 analyses. Right? So if you're looking at the slope of CC10 predicting performance, you have 100 different standard errors of that slope. You square those, sum them together, divide by 100. That's your standard error. Right? And so the square root of that term represents the estimated standard error, ignoring imputation uncertainty. Now, the between imputation variance is literally, if you take all the 100, not the standard errors of your estimates, but take all 100 slopes that you have in this example, and you calculate the variance of the 100, right? So what I'm highlighted here, and I'm really disappointed in LaTeX moving my hats over. I fixed it and I forget how to fix it, and I don't know. I'll have to figure it out again. This is the point estimate of a slope at for any given data set. This is the overall average across all 100 data sets. So this is simply a variance formula, the variance of each of those estimates, right? And this estimate here, as you might imagine, is part of the reason why we want to have more imputed data sets, right? because the more imputed data sets we have, the more analyses we have, the bigger, the more precision we'll have to estimate this variance. That's part of what we do. So the total variance then is equal to the within plus the between plus a correction factor. This correction factor goes away as m goes to infinity. Right? Any questions on that? But again, I don't want you to memorizing these formulas. If you're in a spot where you need this, someone's probably already created this for you. Or if not, hit me up. I give you a lifetime license to email me from any time you like. It happens. All right. The only problem is you have to deal with me in my email. All right. So the pooled standard error then is the square root of the total standard error. And that's what you use if you want to form a like a Wald test for your point estimate, right? What's a Wald test again? You take your average slope divided by its average standard error. You compare that to a z distribution if you wanted to. Okay? All right. Who wants to see this in practice then? Now, I'm finally happy. I think you can do this and it'll matter for all of your data. So I'm finally happy with this. All right. Not that I'm happy with my code. I'm not trying to brag about my code sucks. All right. I'm just going to admit it. But I'm happy that I'm telling you something that I feel is practical because I feel like we haven't had a lot of that in this class. Okay. So let's start with that. The mice package is what we use. Mice has a very long history in R. You can take a look at the number of people who contributed to it. It's quite long. It's a well-maintained package. I don't think it's going away anytime soon. It's done pretty well. I had you use mice before to figure out the patterns of missing. That's our missing data patterns right there. You can see there's 16. There should be 16 total patterns. I don't know if all 16 were observed or not because we have 4 variables and they're either missing or not. So it's 2 to the 4th power is the number of patterns we can have. Here, what we have to specify in mice is the method that we're using to impute the data. So mice actually has a function called make.method, and it starts by doing PMM, which is, I believe, predictive mean modeling, something along those lines. That's what it calls linear regression, in short. But we know female doesn't fit that, so we're going to use logreg or logistic regression for female. And when we do that, the only catch we have to do is we have to convert female to a factor variable. In R, a factor variable sort of hard codes the categories. So mice will run just fine without it being a factor variable, but it gives you a warning. We just fix it as a factor variable to make sure we don't have that warning. I didn't go through the mice code to figure out what's needed. So now, mice, we can actually run the mice function. And what I wanted to show you was the help. Like, you know how I always have to call our help as help, right? It's not really help. And the reason for that is it's hard enough to write the code, and then you have to go and write help for the code. Like half the time I'm writing in our package, I don't even know if the code's going to run. I don't know if I need help myself. But anyway, um, here are a couple things. Number one, M is the number of imputed data sets you're getting. Okay. We saw method before right there. Max IT is the number of iterations. I think that's the number of iterations total. So in this case, what we're going to do is run 10 iterations and take five data sets from it. Let me tell you right now, not a good idea, but I'm going to show you why I'm doing 10 for class. Okay. So here, let's just run that real quick. What you'll see it doing is literally for each iteration, it goes and imputes 1, 2, 3, 4, 5 data sets. So here, what's happening is in each iteration, I misinterpreted what the imputation is. It's imputing 5 data sets with one set of regression parameters. So each of the iterations is a different set of regression parameters itself. Now we can summarize the values, right? So we have 5 imputations. But let me show you what happens if you want to run it a normal amount of time. Let's put 100 imputed values and maybe 1,000 iterations, this is what it's going to do. It's going to take a while. This makes great for great class, makes for great entertainment. Then I'm going to stop it. Nope, stop it. We don't need to see all that. But please, when you do your analyses, make sure you run large number of iterations and grab lots of different imputed values. So here, how about I'll do 50 iterations within each, grab 100 data sets of that 50. Okay. So now it's going to take a bit of time. I'll show you what we do when we're done with this. Almost there. There we go. Okay. So there's our summary. There's our summary statistic of our imputed data. I wanted to compare that with you to our summary statistics of our original data, right? Now, there's not a lot we can derive from this, but we can sort of see this is the complete data. The mean of our complete data is 50.29. The mean of our imputed data was 51.08, for instance. This is for the use variable. When you see that, does that worry you? Why is it different? It is higher, number one. Remember, this is complete data. So in complete data, we have the bias due to missingness, potentially. So what happens is there's a different n for each of these variables, and we know that missingness, those missing values, are not completely at random, right? Because you can go to the top of my code and see that I made the missing values related to other variables in the data. So what we've done with mice here is we've gotten a different mean from it, but part of the reason we have a different mean is now we're imputing on all the variables in this analysis. And we're trying to remove the bias due to the missing at basically the results you see at the top should be accurate with the missing at random assumption. The results at the bottom is like the missing completely at random. And depending on the variable, there may or may not be a little bit more deviation. Like CC10 is the second decimal place. Performance is like the third decimal place, or second. I'm sorry, yeah, second for both of those, and then there's 64% female here, and I think it was a little bit higher in the original data, although it doesn't spit it out because it's a factor variable now. Factors do not get summaries. Come on, R. Questions on any of this? Does this look interesting? Kind of cool? All right, the other thing I was going to do was compare and contrast. Of course, my figure margins are too large. There we go. That's our original data, and this is our imputed data from one data set. Original, imputed. Now, it doesn't exactly look the same, but this is what's happening. And here, this imputed data itself, these are the only the values that were imputed themselves. So it's not going to look exactly the same. And that's why you end up seeing it look a little bit sparser. That's because that's just the imputed values. But one thing I was trying to note with this is the range of values for the original and the range of value for imputed, they're sort of imputed was within that range still, even though we didn't specify it to be like that. It just happened to be part of the process. The other thing I wanted to show you was if we took a look at the original data, that's our relationship between usefulness and CC10. Here, usefulness is on the y-axis, CC10 is on the x-axis. And sorry, this is our imputed data. And this is the original data. Sorry, this is not, pardon me. This is the original relationship right here. This is one imputation of mice. And so I overlaid the blue and the red line on top. And what you're seeing is my imputation didn't really change our relationship. So it's trying to maintain the relationship in the data, but give you imputed values that um, seem to be more appropriate for what you're doing. How are we doing? Sound good? Okay. Let's see where I'm at in my presentation. Of course, I went back to start. That's what I'd like to see. Okay, I'm going to go through the next bit of slides, and then I'll come back and give you the full analysis with mice when we're done. Okay? So here, now in the chapter, it talks about a couple different variables. I'm blanking on what RAV is. Fraction of missing information is FMI. And again, my notation. Excuse me. I don't know why it's repeating things after I switch. Basically, the idea is if we wanted to quantify the impact of the missing data on our results, there are some summary statistics that you can compute. If you're publishing this in a journal, you may be asked to talk about that, right? So there's basically two ratios that take the variance components from our imputation process. Remember the variance within chain, the average variance within chain, that's our average standard error. The variance between chain, which is our weighted variance component across, and then the variance, weighted variance between is literally our variance of the parameter estimates across chains. Variance total is our combination of the two with our our little random factor that goes into it. Right? So a lot of times, if you're using software to do multiple imputation for pooling, you may see both of these estimates, which is nice. The relative, there it is, relative increase in variance is how much, what you're doing is comparing the missing data uncertainty relative to the complete data sampling variance, right? So this is basically how much bigger is between versus within. The interpretation of this is the proportional increase in variance, right? So this is how much variance has increased due to the missing data, compared to the variance expected if there were missing data if the data were complete. So why do I say that? Well, if the data were complete, this thing at the bottom, that variance is a constant, right? There is no variance. It's always the same standard error, right? Sorry, excuse me. The numerator is always standard error. Within is not. So an RIV of 12 means the missing data, or 0.12, means the missing data inflated the variance by 12%, meaning this, my imputed data added much more noise. I don't think that's a problem personally, because when you impute data, if you're doing it right, you should be putting more variability into the analysis, because your missing data reflect, your handling of the missing data is uncertain also. So everything you're doing to your data, you're trying to take the error and not let it propagate through the system. Right? If you imagine the same process and we didn't use the chained equations, but we just did single imputation, right? We wouldn't actually be able to increase the variance at all. It actually reduces the variance. And we say that's bad, right? Well, if we handle missing data correctly, what that means is we have more uncertainty in our model because we don't know what the missing data should have been in the first place. And to do analysis correctly, we have to remember that that means we don't know the values for these. The fraction of missing information compares the missing data of uncertainty, which is the variance between analysis, adjusted for a finite n, relative to the total variance. And this is like an R squared, right? It represents the proportion of total variance in the estimate that's attributable to the missing data, right? So one is how much did the variance go up? The other is how much of the total variance is because of the missing data. So those are both helpful quantities to talk about how much information you're putting in, how much variation you're putting in just because of the missing data handling that you're doing. That's useful, right? And this formula for fraction of missing information with a large N looks like that. But there's problems with that because of the finite M approximation to it. And so here you have to sort of adjust it, which lines and lines of research, long running research program about this, right? Goes way back, way back. So couple caveats on interpretation here. An FMI of 0.11 indicates about 11% of the total variance. The parameter estimate is due to missing information. But FMI is not the same as percentage of missing cases, right? In fact, it may not even be related. If variables are highly correlated with good prediction, you may have smaller FMI, right? What's happening, and I can't go back to my iPad, although I wish I could, is that chained equations, depending on how good the prediction is at each chained equation, you may not have a lot of error around what you're predicting or imputing. That's where this would go down, right? So to calculate this, though, you do need a very large number of imputations, much more so than you might need for adequate power. So if you need more and more and more of this, that's something to think about. Again, I don't know how common this will be that you need to use it, but if you do, if you run into this issue, if you start to have to publish, you know where to look for resources in the book, at least, and otherwise. Now, if you want to go and pool test statistics and confidence intervals, you can do that. The T statistic here is pretty straightforward as we had before. It's our pooled parameter estimate minus perhaps zero, right? Or whatever your idea what the hypothesis should be over the pooled standard error. Now, each of those, again, is the pooled, not the straight standard error that's averaged, but the pooled one, the one that we had to compute with variance between various within. Our degrees of freedom looks like this, much more complicated, but you can compute it, right? Involves the reduction in variance itself. Sometimes this degrees of freedom, though, can exceed the sample size or the complete data degrees of freedom. And so when that happens, you may, instead of using T, it may just be in a Z-test situation. Remember, the T-test effectively becomes a Z-test when degrees of freedom gets to be like 25-ish or something like that. So this may not be a big deal. And of course, there's different ways of calculating degrees of freedom, but we don't need to go into that. Depending on the software you use, you might see T or Z. You've seen that before too, though, right? In Lavon, it's all Z. You could run a linear regression in Lavon and get a Z statistic, right? And the reason for that is it doesn't go and calculate what the T degrees of freedom or the T test should be. It's simple to do in maximum likelihood. Use LM, you get a T statistic. Well, that same thing happens here, depending on the software that you use. Similarly with confidence intervals, the confidence interval will use your critical value for T, but the pooled estimate of your point parameter and your standard error. So you need to make sure that you have pooled estimates again to make this work. How's that going? So far, so good? Okay. Important note, I don't know how important, but we'll find out. It's the important. Uh, we don't want to average our confidence limits. So like you think of these 100 data sets, if you wanted the confidence interval on each of the parameters, you have 100 upper bounds, 100 lower bounds. We don't want to use averages for those, right? Using the T statistic here with the pooled estimates is the right way of doing it, right? Otherwise, you might ignore how much imputation uncertainty is, right? You're ignoring the between analysis imputation there. All right. I am right about break time. How about we take a 10-minute break here? Got a few more slides and I'll dive into the analysis section late after that. Oh, one other thing before I get to break. I said homework's due Friday. It's not due Friday. It's due next Tuesday because I'm an idiot. I apologize. Sorry. I lose track of all, like I've lost my sense of time and place for some reason lately because I feel like all I do is just work and sleep and maybe eat a few times too. So it's kind of difficult for me to step that back. If I worried you about homework, I apologize, but it'll be due on Tuesday, which means you've got more time to email me or to work on. All right, come back in about 2:30 and we will begin the last part of the practical part of class. And after this, it's no longer practical. I'm just kidding. See you in about 10 minutes. Let's get started with missing data. So when might multiple imputation give different answers from what? From maximum likelihood, maybe. From Listwise deletion all the time, right? Because listwise deletion makes much more strong assumptions of your data. But here we can talk about. Um, so there were two different things we can compare here: ML and Bayesian, which are single stage procedures to estimate model parameters, and then multiple imputation. Um, you've just seen the process of. So when will they be the same or different? The difference or the same really depends on the type of model you're doing. Let's just take ML. Let's take a real easy case to see. Not sorry, nothing's easy in this class, but let's take the most simple case. This model done with the SEM approach with maximum likelihood, right? If our imputation model and our maximum likelihood model are the same, we should largely get similar answers. But if you remember our maximum likelihood model, when we had to put things into likelihood, the female variable was binary, and that didn't follow a multivariate normal. But when we go to impute it, we're going to impute it with not a multivariate normal. It's going to be a binary variable. So we might expect to see differences between the two in that sense, right? Um, the other part is where if you have not just what was the word before, corresponding. I think that was it. I got to stop doing that. Sorry about. Don't look. I'll tell you when to look. Congeniality versus correspondence. Congeniality makes you sound like I don't know, nice and friendly. When the models are friendly with each other, when they're basically the same, when the imputation model and analysis model are aligned, then, and by say aligned appropriately, that's really saying, what we saw in this class, the joint distributions are aligned. They may be specified a little bit differently with factored distributions or so forth, but joint distributions, right? So there's a few propositions with this. Multiple imputation and direct estimation use the same set of variables and invoke models equivalent with equivalent assumptions and structure. The result will be that these two estimation approaches should be equivalent. But as we saw, like as I started class by saying, missing data is just a series of roadblocks right now. Like we can sketch out in our statistical theory, we want this joint distribution, and we can, and even if you're not heavy into stat, you can say, okay, I need something that takes all the variables together. But like getting that into your software with your data is the challenge, right? And even when we started with maximum likelihood with the SAM approach, which I would say is the most well-formed of all the simultaneous approaches, that thing had roadblocks, right? We had the binary variable in it. So um, when they're the same approach, same model, same everything, they should be roughly equivalent. Um, there's another case where you might impute more variables. So basically, um, multiple imputation and direct estimation use the same set of variables, but imputation is less restrictive, right, than the analysis model. So in that case, right, if your analysis model may have the same four variables, but you're really only concerned with a couple of the relationships, or imputation model has all of them in, right, then that analysis model is a subset of the bigger model, which is fine. It should align. Uh, Parameter estimates will align. But as you might imagine, the standard errors might be larger in the imputation process because now you've got additional error in that. There's more parameters in the imputation model itself. But now if you have, I've never seen the word uncongenial before. Is there a different way? Discongenial? No. Help me. Morphology is never my strong suit in English. Actually, let's just be real. English is not my strong suit, and I don't really have a fallback. I guess it's like equations. There we go. I can't speak equations. Is it uncongenial? Is that really it? I thought it was. I tried to put it down there. It seemed right. It didn't give me a spelling error. Okay. I just assume everybody else is better at this than I am. So um, the imputation stage, when the imputation stage and direct estimation use different set of variables, that may be bad. Those are not there, and I actually excluded the examples, and then I forgot to change my slide. Um, Another case is when you've excluded analysis variables, right? So if you exclude a variable needed for the final analysis from your imputation model, that's not good. Why is it not good? You know the answer from that from basic linear regression. What happens if you omit a variable that should be in the model? You get a bias, right, of all the other parameters, particularly if that variable is correlated with your predictors. Like if you miss an X, it's correlated with those. Bad. Same thing's going to be bad for the imputation model because the imputation model runs on something you can actually parameterize. You can actually see. And mice makes it easy. You don't have to see it. You could see it if you wanted to, right? So, but we can avoid that by thinking the imputation model is like everything possible. It's the it's the supersize value. No, I don't like that analysis. What's a good? It's like the full buffet. No, I'm going on food. I shouldn't do this. It's going to the car dealership and being like, yeah, I want the maxed out car, right? You want to max out your car for multiple imputation, uh, even if the car you're driving is probably doesn't need to be maxed out. Does that make sense? No, I don't know. I'm trying to give a Lisa analogy. I know she talks about pants and like coals and like, okay, I don't, right? Sorry. If you wanted pants and coals, there's a great professor. She wins awards. She's better at this than I am. Great. But there, I'm going with cars and food. All right. Better yet, maybe this. How about this? You go to the the bar, and you order a flight of beer or wine or whatever your specialty is. But you're not going to drink all of that. But you want your options, right? That's it. Multiple imputation. You need the options. You need the bigger set. Is that better? Are we good with the wine flight? Okay. After after this week, there might be some wine consumed. Uh, After this class, no, I'm just kidding, but not during because this is serious. Another uncongenial case is where you have extra auxiliary variables, but again, that's like the wine flight. This is actually pretty good. Um, Differences will appear, but if you put a lot of auxiliary variables in your imputation model, then you've imputed data with the full general idea, but your analysis model may not have them in. That's okay because your imputed data now are based on the broad set of variables themselves. So you will get different results. All right. Would you like to see all of this put together into one analysis? Okay. Let's do that. Let's see here. Going back to my original data, I'm going to impute. Now what I'm going to do is here, I'm now going to the analysis with all my variables. All right, my analysis itself includes all these variables right here. Right. So what am I doing? I'm predicting performance and usefulness. I'm predicting each of them with female and CC10. And auxiliary variables are HSL, MSC, MAS, and MSE. Things we've seen probably too much this semester. I hope this was not a terrible example. I remember being in stats class and someone was talking about, literally, I kid you not, a textbook had the width of shoe soles. And that was our example all year long. And I was like, my God, if I have to think about shoe soles again, the bad thing. This at least is like I tried to find an educational path model that, we're in education. Well, at least I'm in, many of you are students in education. Maybe that would work. Anyway, social science variables, all that's good, right? Anyway, so now what I'm going to do is I'm going to take 10 iterations. I'm also going to impute 100 data sets from mice. Whoops. There we go. So mice is going to do its thing running. Let me talk about while it's running, what I'm going to run then when I'm done. There's my analysis model. That's our first one. That's what we wanted to start with. And missing data got in the way, right? So in many ways, this is pretty awesome that we can go back to it. Now you'll note, is female in the likelihood? No. Does it need to be? No. Why? every data set we're going to run with this is complete, right? Now, the variables that we've imputed, we have to trust that are imputed correctly, but it's a complete data set. Same thing with CC10. And you'll remember when we first started putting the variables in the likelihood, that's where we started running into roadblocks with Lavon, because Lavon doesn't have ML estimation for a female. It has to use weighted least squares, and that doesn't use missing data. And so we had to go all this other stuff. Well, now we go back to this, and that's great. Now, rather than run 100 different Lavon analyses, the Lavon.mi package, I think Terrence Jorgensen is involved in that. He used to be a student at KU when I was there. He's in Europe now. He's does some really good work with SCM tools and so forth. This package will take your Lavon model and apply it to each of the data sets in your mice output. And the nice thing about it is you don't have to reformat your mice output. That mice output that we have right here contains all our imputed data sets. So we don't have to worry about transforming things or anything else. We can just put this into Lavon. Oops, did not run my code for this. Takes a bit of time to run, as you might imagine. It's running Lavon 100 times. But now the summary statement will look very similar to what we see in Lavon. Where did it go? Oh, it's taking a while to do. Anybody want to guess why it took a while to run summary there? See how long it takes? Oops, I was summary. Because Lavon.mi is doing all the pooling for us too. So it's pooling all the standard errors, it's pooling all the parameters, and it's giving us appropriate test statistics. And so what you end up seeing here are what the result of the process. And that, how do you know that's the case? Look, there's degrees of freedom that have fractions to them. Like when you originally learned statistics, degrees of freedom was like simple, right? It was the number of possible things you could change and still have different data. No one ever told you to get fractional degrees of freedom, did they? But sure enough, you can. Where else have you seen fractional degrees of freedom? Anybody seen it before? In a multi-level model, because in multi-level models, these parameters, depending on the dependency in the data, degrees of freedom is not n minus number of parameters. It's the n that's the effective n, right? Once you control for the interclass correlation. And the methods for doing that try to basically see how much correlation there is in your data and adjust them as if they were independent, right? So that's that. But here are our estimates. And not only are they estimates, the beautiful thing about this is they're on the scale that we wanted them to be. They're directly interpretable. And you could take this output and interpret it just like you would interpret Lavon output for one analysis. There you have it. To me, that's awesome. How many of you can run your model? You know, I asked you to provide an example of your model. Most of you, I think, could use Lavon for most of your models, if I'm not mistaken. Right? Have you thought about it? I mean, maybe you want to choose a different package. There may be multiple imputation versions of those packages as well. Right? Because once mice was created, everybody was starting to attach to mice. There's another missing data package called Amelia. It works very similarly. I'm not an expert in it. I'm much more familiar with mice, so I didn't choose to show it to you. But and not only that, if you wanted to see the parameters themselves, here are the parameters. Yes, that's right. That's right. So the random number seed, there's no such thing as a random number in our computing environment. What the seed does is it sets a chain of random digits. So every when you set a seed, you basically set what the random digits that come out happen to be. That doesn't mean they'll all be the same, but what that means for mice is that every time it draws a random number, it grabs the current value of the seed from this chain and uses it to calculate the random number. So when you start with the right random seed, and the process is the same, and the architecture is the same, you should get comparable, similar, same results. It's not always the case because parallel computing treats seeds differently. And if you specify your order of the sampling different than mine, this you may choose a different number. Like so, for instance, if in mice, I don't know which how I didn't get under the hood of mice to see how it works, but if mice sequentially generated data and performance was first and usefulness was second in my data, but it was usefulness first and performance second in your data, then even the random number seed won't be the same. But for the same seed, the same code, and the same computer, you should get the same results. Does that help? Yeah, so seed itself, you can set it with a random number, an actual number. If you don't like doing that, it seems arbitrary to you, and it is, but you can set it based on, uh, oftentimes what a computer will do is take the number of like milliseconds in the day and set it based on system clock. So it will initialize a random number seed that will at least allow it to be replicated, but it won't be something you have to pick, right? But yeah, 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 it's okay. I don't. Uh, to the extent where you'd have to use either in the first place, no. The difference is with the complete data, you don't have to worry about entering the missing data variables into the likelihood function. And so, in theory, they should be the same. But again, we've seen data analyses where you still have to do factor regression without having to put things in the likelihood function. So I can't say it's always going to be the same. It depends on your analysis. But for this example right here, Levon allows me to use, where did it go? To specify a multivariate model with my joint data, and that would be just fine here. That I don't have to factorize it, right? That help? Yes. Mhm. You can. Um, Levon, you have to create a new variable that's the product of the variables. Um, so what that means is you'd have to go into your mice output here. Oh, so that's the original data. Let me just inspect the nice output. It's a list. Actually, how long is the list? Oh, that's the number of variables. You have to go into mice and grab the, nope, that's not it either. Basically, for each data set in mice, you'd have to go create the interaction. And there's likely a way to do that. Nope, that's not it either. There's likely a way to do that I'm not familiar with. But basically, you could do it. You just have to go for every one of those imputed data sets, create the interaction, and use that in Levon. Yeah. Other questions? Okay. You want to see how this compares to our model where we take everything and put it in the likelihood function? So this is the complete data model here. And our maximum likelihood gave us the warning that one variable's variance is 1,000 times larger than the other. That's what happens with the binary variable. Missing data not fit. That's the wrong summary. There's our summary. And let me compare and contrast here. Let's see. So this is the results with missing data. And I'll compare that with the results with observed data here. I did not put, this is actually where I didn't put the variables in the likelihood. So you see these zero values here, they're fixed because Levon imputed their sample means. So our missing data version, like our intercept estimate of performance was 14.5 with a standard error of 3.2. But when we do our multiple imputation, the estimate's actually now 16 with a larger standard error, right? And what you're going to end up seeing here is not always the case the standard errors are larger or smaller, but look, the point estimates have changed as well too. They're roughly the same, but not exactly. And if you take a look at like our variance estimates, the variance of use is much larger in our missing data approach, and the standard error is much larger. But then again, the the variance of performance is actually a bit smaller. So it's not exactly the same. And part of that's because I'm using what I'm comparing here is this is our imputed data right here, and this is our data with incomplete data. Actually, I got the direction wrong. Uses is much smaller in imputed data. So it's not always the case that you're making things worse, potentially, variance wise. But this to me is so much easier. So, other question. Did I answer your question? I don't know if you asked that. Maybe you did. No, never mind. I'm out of my mind here. Okay, just looking at 11% gain in the stock market. What the heck's that all about? Anyway, so what do you think? Yes. No, no, this is not because this is in Levon. It's just assuming it's a variable. It doesn't have a distributional assumption to it, right? So we didn't put this in the likelihood or any of that. And actually, that is where I put the last part here. This analysis in the likelihood here. I wanted to look. Nope, that actually didn't work either. Yeah, it's not doing what I expected to do. So I'm gonna ignore that last part. But here, long story short. So what do you do with missing data? Missing at random. We've gone through the three approaches now, right? ML, Bayesian, mice, multiple imputation. What do you do? For me, I like mice the best. If you have a model that fits into Levon and you can use Levon.mi or some other package for it, I think it works great. You could do mice, hardly change your data, hardly change anything. Go into ML, Levon, run your analysis that's pooled, get pooled estimates. Now, where are the problems with this? Number one, if we didn't specify the imputation model well, but that's always going to be a problem, right? But number two, there's no problem. I mean, this is the literal model you wanted to run in the first place. So to me, that's great. That's the way it should be, right? Hooray. So we went through all that hard part to get to the easy part, which is multiple imputation. And what I anticipate doing once this homework is over is one more homework for this semester, one more, and it'll be on multiple imputation. Okay? And I imagine that will go much faster for you because there's only so many ways I can ask you to multiply impute my data. It's still going to be the same example that we sort of been nursing along throughout the class. So I'm hoping that'll go a little bit better for you. But to me, if you can get multiple imputation working, it's likely to preserve most of the relatively easy parts of your model and be approximately correct. Yes, you may still have problems with whether your imputation model is right. Well, you may have problems whether the actual model is right as well too. Right? There's all sorts of ways to worry about this. Now, one thing we don't have to worry about because I've specified this model where it's saturated is we don't have to worry about model fit statistics in it. If you can saturate your model, that would make it even better. But not always can you do that. So of the three methods, which one do you like best? I just loaded the question. How many of you say ML, straight ML, everything in the likelihood? How many of you say Bayesian with Jags? I'm going to put you two together and talk. uh, all right. How many of you say multiple imputation? Hooray, 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 hooray. Cool. Um, Big picture, I think, again, the nuances of missing data, this version of this book does cover a lot of the nuances. But the problem with the nuances is it loses the practical application. If you focus on this, it works. Now, this helps with data that are missing completely at random or missing at random. But if you got missing not at random, how would you know? Number one, probably won't. And number two, what do you do about it? Well, that's a later chapter as well too. And it's not a good answer to that one either. But this at least gives you a good chance to get in the right ballpark for most of what you're doing. Is it approximate? Yes, for some models. This model is actually not approximate because we only have one binary variable, a bunch of other complete variables. So it's a comparable joint distribution that we imputed on. Cool. All right. So I don't think I have many more slides than that. I left off in the 70s, number 80. So, and again, I have. So multiple imputation focuses first on creating suitable imputations for later analyses. It sort of divides the process up. Ideally, I wish I could take the pooling phase out of it. I have this hunch, I have this probably a bad hunch. Whenever I have this hunch about like quant methods, 1 out of 100 is true. So just take this for that my hit rate on this. But um, I have this dream where you could take the multiply imputed data sets, stick them in JAGs. I think I told you this, and then sample which data set to use at each iteration, thereby combining the pooling phase into one thing as well. And because the data are complete, then you can use the joint model and joint distributions in JAGs and get the same parameter specification. But that's remains to be tested. I also have this dream where you could impute data in Bayes and do your model, have both simultaneously. And in some cases, I'll bet you can do that, and people are doing that, but not always. But um, I still like this approach for multiple imputation, particularly if you're going to use maximum likelihood based estimates. Multiple imputation fits well. If you're doing Bayesian, it's a little harder because again, you're now having to talk about running Markov chains on all 100 data sets, and every data set you have got. Let's say we have 4 Markov chains. Every one of those has to converge, and then you pool within. Do you pool between? I don't know. Maybe not. So I've got some ideas, Bayesian ideas, or I'd like to learn more about this, but that's where I'm at. But basically, I think this is pretty practical for what you're going to do. I expect if you're going to use missing data, you'll probably start here. That'd be my recommendation. And if there's a roadblock here, then you'll have to branch out and think of something else. And again, I give you the lifetime warranty. If you have a problem, you can find me, find my email. There you have it. Hit my YouTube channel up, put a comment in that's mean and aggressive. Can't believe you didn't teach me how to handle this. It'll be like the bat signal. Yes, how can I help? Um, Now remember, agnostic. I only showed agnostic imputation here. It's sort of like I'm not a fan of the model-based imputation. I've seen it in places where people are really excited about their results. Like it just doesn't seem like the fit with science, right? Which is I'm going to try a model that I'm not certain is the right one, but then I'm going to make my missing data look like what it would have been under this model. And then I'm going to pull all my results together. And guess what? My model looks like it's pretty good, right? I don't like that approach, but sometimes it may have to be used. But just be mindful of that. Like, for instance, how many of you do the package MERT in here in IRT? Turns out MERT has functions for multiple imputation. Did you know that? You can impute data with MERT, but it imputes data on the model you specify. And where I've seen it used is MERT will not give you some of the model fit it does really well, the like the M2, without having complete data. So the solution is, well, impute the data and then go do model fit. Well, guess what? If you got a lot of missing data, you just imputed data that fits the model. So now your model fit includes all the data that fits the model. Your model fit looks amazing. And I tell you this from first-hand experience. I had to do it once. I was working on a project with a country in the Gulf state area. Uh, you know, yeah, you know what I'm talking about, right? That Persian Gulf area, right? And and they're like, "Well, just do this." I did it. I'm like, "Oh man, everything looked great." Yeah, it's because it was imputed with the same model. So a lot of times, imputing with your same model, the agnostic approach is my thing because it is my recommendation, not just my thing. It's if you can find an agnostic approach, how would you build it? Okay. All right. Any other questions? Yeah. Right. We are using a random draw of 50 from the whole process. Right. So each iteration is doing data sets, but then once you get the whole thing together, you've got, iteration times whatever from it. And that's where we're drawing it from. So that help? We could be, but mice will select 50 out of the 5,000. Yeah. Yeah. Yes. That's how we interpret them. Yep. Yeah. Basically, we look at these results right here as if we ran Levant, as if we had complete data to begin with. Where's my, let me just grab these one more time. So, oh, look at that. We ran Levant. Here's my Levant results. We interpret them as if it were complete data, and this is what we were to find. Does that work? I think that's good, personally. Yeah, makes it a lot easier. All right, other questions? Mhm. So in mice, you can sort of, it's harder to understand, but it defaults to a model like I tried to draw on my iPad, which was each variable is predicted by each other variable itself. No interactions, all main effects. And for the female variable, I had to specify that was a logistic regression. So it treated it as a Bernoulli distribution to impute it, conditional on all the others. And so if I were to look at mice output predictor matrix, basically this matrix is telling you when perf is being imputed, what are the predictors of it? It's all the ones with a one. Does that make sense? And so what you see here is that means they're all main effects. They're not interactions. There's no curvilinear effects, any of that. But each variable is predicted by all other ones as well. So that's your imputation model. And so this is, I would call this an agnostic model, right? Because if I was not doing agnostic, then I really have the four variables of my model itself only. But because I have auxiliary variables, I put them all in. And the auxiliary variables, as you might understand, I mean, now we have, instead of having four variables or three variables predict each outcome, like performance was only predicted by the variables in the model, there'd be three. Now it's being predicted by seven. And what you would think is that that seven should improve the prediction. And this relates back to, I want to say one other thing. I'm on a tangent, but I think it's relevant. The auxiliary variables here, if you're thinking about how many auxiliary variables to add, well, think about this. How there's sort of a diminishing return. If these are correlated, how many do you need? How many makes it better? In the original, like first couple chapters of the book, they were like a handful, not a lot, maybe two or three. The best ones, there was the homework assignment where we had to figure out which auxiliary variable might be best. you might be in a situation where you have to choose what variables to put in. You may have 30 variables. The other way that you could do that is try to do a data reduction technique on the auxiliary variables, reduce them into like principal components, and put the principal components in, because the principal components will be uncorrelated with each component, but potentially correlated with the other variables in the model. But yes, so model agnostic, that's the model that defaults to it. There are options, I believe. I'm going to mice. There are options where you can specify the model formulas as well too. So you could change that imputation model if you wanted to as well. Okay. I didn't show that because your what you might do for change it may not be what Ju Young does, may not be what Eric. It's very idiosyncratic. So I can't give um, a general approach, but that's this approach right here is agnostic, and it's built to be bigger, and that's why most people like to use it. I hope that helps answer your question. Other questions? Yeah. Yes. Yes. You can use that in mice as well too. Uh, that's right. And I am blanking on where that is right here. But yes, there's an option for how to specify it. Logreg may do it because it looks at the factor itself, but it's been a while since I've tried it and I didn't put this in the example. So sorry about that. Mhm. How many of you are going to use mice then? Yeah. One thing I gave you. One. All right. Anything else then today? You get out early again, although it's like 12 minutes then. All right. 12 minutes early. Have a great rest of your week. Um, buy the dip in the stocks. Just kidding. Yeah, what's that? Yeah, exactly. Exactly. Stay out of the stock. I don't know. It's consult your financial professional for advice on how to navigate the market. Have a great rest of your afternoon and stay away from the news. Take care.